So before I dive too much into this topic, I would like to acknowledge the excellent talk by Matt Westerby earlier in this lecture series. Matt provided a really comprehensive overview on the anatomy, the impacts, and also the potential for disaster risk reduction for glacial lake outburst floods. So to avoid some of the redundancies, especially for those of you who attend this lecture series often, I will just give a very brief introduction on the topic of glacial lake outburst floods. And instead, I would like to focus on a method that may allow us to objectively estimate GLOF hazard. Next, I will then present trends in global and also regional GLOF hazard for different mountain regions around the world since 1990. And finally, I will also discuss potential reasons or drivers that might explain the observed trends in GLOF hazard. So I'm interested in high mountains because these regions are thought to be especially prone to climate change. Many scientists believe that climate change will alter natural hazards that evolve in high mountains and put the downstream population at risk. Glacial lake outburst floods, or GLOFs for short, are one of the textbook examples for this hazard cascade. This photo here shows only one of the many thousands of glacial lakes that we find today in world's high mountains. With this cartoon, I'd like to show that such glacial lakes can also be a hazard because they can fill with meltwater from the glacier and suddenly, without any warning, they can burst out. And the result is a catastrophic flood that moves down the valley, transports huge amounts of sediment, and covers the entire valley with debris. This is also what you can see here in this picture. This is Lake Dikcho in Nepal, which also has burst out in 1985. So, what is actually the logic to believe that GLOFs are becoming an increasing hazard? In recent years, temperatures have increased and glaciers have melted and retreated rapidly in virtually all mountain regions of the world. At the same time, glacial lakes have filled the new space that the retreating glaciers have created. This time series shows Imja Lake in Nepal, which has more than doubled in area over the past 30 years. The growth of these lakes is by no means an isolated local phenomenon. This map here shows that the total lake area in the Himalayas has increased by about 14% between 1990 and 2015. In the central Himalayas, lakes even grew by 23% in that period. Outside of the Himalayas, we find very similar patterns of lake growth. In the northern Andes of Peru, for example, we can see that the total lake area has increased by about 25% since the middle of the 20th century. In Northwest North America, lake areas in Alaska and parts of British Columbia have increased even by 59% since the mid-80s. This increase was mostly driven by moraine-dammed lakes, which even grew by 87% in this period. Distinguishing between these different dam types is important because they may tell us how stable these lakes are and how long they might persist in the landscape. Moraine-dammed lakes are often consist of loose debris, and they can collapse suddenly, mostly once in their lifetime. Some lakes can be dammed by thick glaciers in side valleys, and these ice-dammed lakes can drain through a tunnel at the bottom of the ice, which can seal after the flood so that the lake level can fill and burst out repeatedly several times. Lakes in bedrock have more stable barriers, but they can be overtopped, for example, by landslides or ice avalanches that hit these lakes and overspill the barrier. When these dams fail now, they can release huge flood waves that cause a lot of destruction on the way downstream. The GLOF at Kedarnath, for example, in India, buried an entire town in debris and killed several hundreds to thousands of people, according to estimates. So many scientists hypothesize now that larger lakes could increase the hazard posed by GLOFs. Larger lakes are thought to have greater depths and also greater volumes, which may cause possibly larger flood magnitudes and damages if these lakes fail. Now, how this change in hazard can be measured objectively was actually hard to find in the literature on GLOFs. My goal was therefore to work on a more consistent approach to quantify trends in GLOF hazard. So the way researchers have commonly estimated GLOF hazard is to define a set of variables for each lake, which might indicate the stability of a given lake. These variables may include the lake area, the steepness and the size of the catchment, or also the steepness of the dam. And each lake can then be ranked from the highest to the lowest value in each of these categories. These ranks then serve to qualitatively classify each lake as having a relatively high, medium, or low probability to burst out, and also to categorize then each lake as a critical, potentially critical, or not critical lake. Finally, all these lakes can then be grouped across basins according to their hazard class. I think maps like this one here are interesting and useful because they provide a very general idea where to focus more research on GLOVs. But on the other hand, it's important to note that the outcome of such a hazard classification varies from study to study because every study may use different input variables or also different thresholds for classification. So the question that I had was, isn't there a more objective method to define hazard, where we could express hazard, for example, not by subjective classes, but as the probability of observing a GLOV of a specific magnitude? Such a definition of hazard is not new, of course. Hydrologists have been using probability theory for decades now to estimate flood hazard. Their approach involves usually to define a study region and a study period, and collecting the floods with the highest flood stage or the highest flood discharge or the highest flood volume per year. And finally, they fit an extreme value distribution to these annual maxima. That distribution then has certain parameters that describe the location of the distribution, the shape, and also its tail. The tail is particularly important because it tells us something about the exceedance probabilities of a specific flood magnitude. For example, a flood that occurs on average every 10 years has a 10% probability to occur. And a flood with a 30-year return period would have an exceedance probability of about 3%. We could do this basically for every desired exceedance probability and obtain a continuous curve of return levels here on the y-axis for a given return period for our annual maxima. However, if now these annual maxima change over time, our extreme value distribution may also change. For example, if discharges increase over time, then this distribution might shift to the right, which would then correspond to a higher return level for a given return period. So to achieve this, we can simply allow the parameters here of the extreme value distribution to vary with time. This would then allow us to test if the estimated return level from an earlier period would be higher today. And in the rest of my talk, I will mostly talk about this 30-year return period, which is equivalent to the common climate reference period that we use in climate sciences. So how can we now transfer this concept from river floods to estimate changes in GLOV return levels? Obviously, the most important requirement is a GLOV catalog from which we can extract the largest GLOVs per year. We focus here on 13 mountain ranges on 4 continents, that is North America, South America, Europe, and also High Asia. And within these regions, we reviewed more than 800 sources of information, such as scientific publications, reports from local agencies, accounts from social media, remote sensing datasets, or articles in newspapers. And we selected from all these sources only GLOVs that had a reported date or year, and we also validated each GLOV using satellite images. And in summary, we collected more than 1,500 dated GLOVs from ice, moraine, or bedrock dammed lakes that occurred since 1990. Our database shows that ice-dammed lakes produce most reported GLOVs globally. About 92% of all GLOVs that happened since 1990 came actually from ice-dammed lakes, while only 8% came from moraine and bedrock dammed lakes. The pie charts in these 3 maps show that ice-dammed lakes here in blue were responsible for almost all reported GLOVs in Northwest North America, in Patagonia, and also in the northern parts of high mountain Asia. Failures of moraine and bedrock dammed lakes have been reported less of. Only 3 regions, the central and northern Andes, the Himalayas, and Tibet and Hengdu-Anshan, had more than half of the reported lake outburst floods from moraine and bedrock dammed lakes. So besides occurrences, we also need an indicator of GLOF magnitude. And we choose here the lake area immediately before the outburst happened as an indicator of GLOF size, because that might also be a good proxy for flood volumes or also flood discharges. We mostly used Landsat and Planet images to map the area of each of the 1600 GLOFs in our inventory. The example here shows that the area of this ice-dammed lake in Patagonia shrank by about 10 square kilometers just right after the GLOF in 2022. What we find is that ice-dammed lakes produce much, much larger GLOFs than other lakes, which you can see here by the size of these transparent bubbles. The blue bubbles are the areas of the ice-dammed lakes, and the orange one are the areas of moraine or bedrock dams just before their failure. On average, the area of ice-dammed lakes before the outburst is about 10 times larger than that of moraine or bedrock dammed lakes. And then we fitted an extreme value distribution to the largest of these GLOFs to see how the 30-year return level has actually changed between 1990 and today. What we see is that all of the largest GLOFs per year actually came from ice-dammed lakes, which makes them actually the main driver of the global GLOF hazard. This graph here shows the largest burst ice-dammed lake on the y-axis versus time. And the points show actually that most of the large GLOFs per year occurred in Patagonia and Northwest North America. None of them actually occurred in high mountain Asia. And the blue line here is what we are mostly interested in. It shows that the 30-year return level of ice dam failures has increased by over 50% between 1990 and 2023. Today, the global 30-year return level of an ice dammed lake failure is about 33 square kilometers. Just to give you a visual example, that amounts to the area of 25,000 times the area of an Olympic swimming pool, which is quite some, right? For moraine dammed lakes, we found no trend in the return levels. On average, a moraine dammed lake of about 3 square kilometers bursts out once in 30 years, and that's about 10 times less than the corresponding return level of an ice dammed lake failure. We also find that the most recent GLOF disasters, such as the GLOF in India that happened last year, had not yet raised the global return level of moraine dam failures. So this may sound like moraine dammed lakes are not super important or that they don't pose a significant hazard. But to make this really clear, I'd like to stress that return periods can be an objective indicator of hazard, yes, but return periods do not say anything about the exposure or the vulnerability to GLOFs, nor do they indicate something about past or potential damages or losses from GLOFs. Instead, return periods quantify the probability of a potentially, and this is a really important word, of potentially harmful processes. This means that an event can have a high return period, but cause little or even no damage. To give you an example, on the left, you see South Lonak Lake, one of the largest moraine dammed lakes that failed during our study period. And on the right is ice dammed Lake Bernardo, one of the largest ice dam failures we have observed in our time series. And just to remind you, both images have the same scale. So South Lonak Lake, the largest moraine dammed lake, was much smaller than Lake Bernardo. The difference between the two events is that the GLOF from South Lonak Lake hit an inhabited valley, killed more than 100 people, and destroyed dozens of bridges and a hydroelectric power dam. Lake Bernardo, by the contrary, directly drained into the steep Bernardo Fjord, and which was not populated at all and caused also no further damage. So the point that I'd like to make here is that the specific given site risk can differ substantially from the hazard posed by GLOF. We also calculated return periods for our 13 study regions separately. If you see blue points and blue confidence intervals in this graph, this actually means that the return periods have increased credibly from 1990 to 2023. And what we find is that only 5 of our 13 regions had actually an increase in GLOF return levels since 1990. 4 of these regions actually are located in North and in South America. The region with the highest 30-year return level is Patagonia, where a lake of roughly 60 square kilometers bursts out on average once every 30 years. That's a lake that would cover the entire area of Manhattan if it fails. The largest relative increases occurred in the coast ranges of Alaska, where the GLOF return levels have about doubled between 1990 and 2023. In other regions, GLOF return levels have changed less so dramatically. In Europe, for example, we only find a small increase in the return levels in Scandinavia, no change in Iceland, and even a decrease in the return levels in the Alps. But the one continent that surprised me the most is actually high mountain Asia. Return levels there stayed constant in all 4 regions. And compared to all other continents, regions in high mountain Asia had also some of the smallest GLOF return levels that we estimated. So even the strong increase in total lake area that we had just seen in the introduction had surprisingly little effect on GLOF return levels. By contrast, the number of large ice-damped lakes seems to have a much greater effect on return levels than the overall lake growth. To find this out, we extracted all lakes that are today larger than 1 square kilometer from previous lake inventories. And what we find is that only 7% of these large lakes today are actually damped by ice. And only half of all regions, mostly again in Patagonia and Alaska, in fact, have such large ice-damped lakes. So this suggests actually that the regional increase in GLOF return levels that we've seen was mainly caused by only a few large ice-damped lakes that failed in our study period. The good news from a risk perspective is actually that many ice-damped lakes will shrink and also disappear if their dams melt away, so that also the return levels might likely drop in the future again. Moraine-damped lakes might behave a little different from that and persist in the landscape for much longer periods. But interestingly, we see that large moraine-damped lakes actually have not changed much since 1990. This graph here shows the fraction of all lakes that grew here in red, that shrank in blue, and all others that remain constant in gray. And what we see is actually that gray dominates in this figure. Or in other words, most lakes that are today larger than 1 square kilometer did not grow credibly since 1990. In Iceland, in the Andes, and also in Scandinavia, none of the large lakes actually grew since 1990. One reason that might explain this stagnant behavior is that glaciers can recede out of their over-deepened basin into steeper terrain, and this in turn limits the storage space for meltwater, and the lake growth slows down. This is what we also see here for these 2 lakes in the Himalayas. So once this time series started, we see as soon as most of the ice has melted, the lake growth slows down and the growth actually stalls. Indeed, we see that more and more lakes actually have decoupled from their parent glaciers as they recede to higher elevation. This example here shows 4 large lakes along the southern Patagonian ice field, and 3 of them have just detached from their parent glacier in the past 5 years. And the other one here, that 4th one, is just about to do so in the coming years. We find that globally already half of all large glacial lakes are no longer in contact to their parent glacier, and therefore their growth might be limited in the future. This decoupling between lake and glacier is actually important because most moraine-dammed lakes have burst out due to ice avalanches from the parent glacier that impacted the lake and generated a displacement wave that overtopped the dam. So the wider this gap between the lake and the ice gets, the less likely is it that an avalanche will eventually reach the lake and also trigger a GLOF. So eventually, ongoing glacier retreat might actually make moraine-dammed lakes more stable in the future. Some of the very large lakes might also persist for tens of thousands of years in our landscape without actually generating an outburst flood. The three largest glacial lakes in our study region, Lago Argentino, Lago Viedma, and Lago San Martin, are emblematic cases for such large and stable lakes. All of them sit in flat depressions in mountain forelands and are surrounded by moraines many hundreds to thousands of meters wide. And if we zoom in a bit here, we can also see that all of them have developed very wide outlet channels that can be many tens of meters wide and effectively route the meltwater out of these lakes. And in fact, more than 80% of all large lakes have developed today such established outlet channels. And I think this is really important because these outlet channels can make these lakes more resilient against outburst floods. Other lakes also lie close to the ocean with little elevation difference between the lake and the sea level. This is Vitus Lake, the largest glacial lake in North America, which sits behind this 2-kilometer wide moraine dam. But that dam actually is incised by a wide outlet channel down to the sea level, so that this lake is actually more like a coastal lagoon. And it's just difficult to imagine how such a large lake can actually breach catastrophically. Finally, also humans can help to maintain or even reduce GLOF return levels. Most large lakes in Scandinavia, in the central Andes, and in the European Alps are actually reservoirs with controlled outlets. These lakes have concrete or reinforced dam, and their water is actually used to produce hydropower or fresh water. By the way, this dam here, the Grand Dissens Dam in the Swiss Alps, was for many decades the tallest dam in the world with about 285-meter crest height. And this lake here is also one of the largest lake in the entire Alps. But such constructed dams seem to be much more stable actually than naturally formed dams. At least we are not aware of any recorded failure of such reservoirs during our study period. A few large lakes also have been reinforced after an earlier outburst to reduce potential impacts for future outbursts. This is the case at Lake Palcacocha in Peru, for example, which began to grow after an outburst flood in 1941. You can still see here the breached moraine dam where the water spilled out of the lake in 1941. Engineers then built here two concrete spillways to absorb actually potential splash waves from this lake, and they also installed pumps to lower the lake level. Such measures may not completely rule out future outbursts, but I think they can significantly reduce their runout, their inundation extent, and also their flow depth. We've seen now several reasons why return levels might not have changed or increased even everywhere. But of course, GLOF hazard could be prone to change in the future. One idea, for example, is that landslide might become a more important trigger for GLOFs, because thawing permafrost could make hill slopes close to lakes unstable. This is what also likely happened at that recent landslide in British Columbia that triggered a tsunami wave that caused a runout of more than 150 meters along these valley flanks. So I think this argument of more landslides into lakes makes a lot of sense. But on the other hand, so far we found only a dozen of landslide-triggered GLOFs since 1990. So I'm not entirely sure whether this increase in landslide-induced GLOFs has already happened. But I think that this is a really important research field where we need much more continuous monitoring of these hill slopes to see if permafrost thaw could potentially lead to more landslides and also potentially lead to an increase in GLOF return levels. One of the greatest concerns about such future GLOFs is actually concerns for safe hydropower production. As of the end of 2022, about 4,000 hydropower dams were currently under construction or planned. And many of these hydropower dams will be built along glacier-fed rivers, for example, here in the Himalayas and also in the central and northern Andes. So GLOFs could be one of the key hazards to this growing hydropower potential in these regions, and they could also be one of the key obstacles to produce clean energy. So besides our regional extreme value models, we also need much more localized hydrodynamic models. Such models will actually allow us to simulate GLOF brownout and also GLOF impacts from very specific lakes and also for specific sites and valleys, so that we can actually anticipate where we expect the highest damages and also the highest losses for hydropower facilities. So to wrap this up, we've seen that GLOF return periods have increased in about a third of all study regions. GLOF return periods are dominated by far by ice dam failures, but they show little response to the overall lake growth that we've observed between 1990 and 2023. So with these ideas and conclusions, I'd like to close my presentation and I welcome any questions. Thank you.